Okay, so today we've got one last little topic as part of chapter 21. And be the end of new material for this exam, and then we'll do a little bit of review, whatever you guys want to practice. All right, so we've done halogenation at the alpha position. We've done aldol reactions, which also happen at the alpha position. And you can also do alkylation at the alpha position. Pretty convenient reaction for installing a lot of different groups. And fortunately, both of the steps you sort of already know. The first is you make the enolate, and then it's just an SN2 reaction. So we'll take a ketone, and there's our alpha hydrogen. Yes. Substitution nucleophilic dual process transition state. Yeah. And then, so we need to make the enolate. So let's use sodium hydride. Sorry, that's an ugly Na+. So we'll deprotonate the alpha carbon. It goes there. There's our enolate. There's another resonance structure of this enolate, as you know, but it's not going to be important for this reaction, although you should still be able to draw it. So see if you could think that out. Okay, so that's step one. And our second step is an SN2 at an alkyl halide. So we're generally going to use bromides or iodides for this, not chlorides. They're typically not quite reactive enough. So let's use methyl iodide. And of course, because you're doing an SN2 reaction, you have to have your alkyl halide follow the rules for stuff that can undergo SN2 reactions. Specifically, it's got to be a primary or maybe a secondary, or in this case, a methyl alkyl halide. And so here we just take our nucleophile, which is the carbanion that attacks the carbon. So there's our carbon-carbon bond forming and the alkylation. And our leaving group is the iodine. And there's our alkylated alpha position and the leaving group ion. Okay, in this example, I've shown a symmetrical ketone, cyclohexanone. And so, nobody was to say that we couldn't deprotonate that hydrogen on the other side, but because they're chemically equivalent, it doesn't really matter. So there's no difference in selectivity between having the methyl group end up on the right-hand side alpha carbon versus the left-hand side alpha carbon. But if we use an asymmetrical ketone, You do that, you need to make sure that you pick the right base, as in sodium hydride or something else, in order to get the product that you want. So let's say now that we start from this ketone, which maybe we made like using the process I just showed you, could do an alkylation there. But let's say we're going to use this as a starting material and do an alkylation. So we can use LDA. That's typically done at minus 78 degrees Celsius. Anybody know why? That's a very specific temperature. Anybody know what that corresponds to? That's the sublimation point of dry ice. So what you do is you get some isopropanol or acetone and crush up some dry ice, put that in the solvent, and it makes a really cold slush bath at minus 78 degrees. And so whenever you see minus 78, that means you're going to do the reaction in a dry ice acetone or dry ice isopropanol bath. Common for really reactive substances where you need to cool it really, really cold in order to prevent it from like blowing up in your face. And LDA is one of those. So use LDA, and then we'll use methyl iodide again. So if we do that, we get this isomer, where our ethyl group and the methyl group that's just been added are not on the same carbon. Or we can do like above, sodium hydride at room temperature, typically, and methyl iodide. This is going to give you a different product. In this case, the methyl group is going to end up on that same carbon. So clearly the choice of base is very important, and it's the only thing that affects whether we get one product or the other. So to explain this, we need to look at the structure of the two bases. LDA looks like that. Lithium. And sodium hydride looks like that. So in order for substitution to happen at the carbons that we've indicated that it does, the proton that gets deprotonated to form the enolate here is that one. And in the sodium hydride example, the proton that gets removed is that one. So based on the structures of LDA and sodium hydride, why does the LDA go for that proton on the left and sodium hydride go for the proton on the right? This is best thought of from the perspective of LDA because it's sort of the more interesting example, at least I think it's the more interesting example. And that's because of all the decoration around the nitrogen atom. So we've got two isopropyl groups. And those groups are fairly large and bulky. So we call LDA bulky base, whereas the hydride is really small. In fact, it's the smallest base you could possibly have, just a hydrogen with some electrons. And so that means that LDA is going to deprotonate the less sterically hindered alpha hydrogen. And so that's visible right there. So that hydrogen, at least compared to the other one in blue that's shown on the second structure, is less sterically hindered because the carbon that it's attached to has fewer substituents on it. And so that big kind of molecule with all of the isopropyl groups on it has a trickier time getting to the more hindered hydrogen in the second example. And so it'll deprotonate the less sterically hindered alpha hydrogen. Sodium hydride is going to deprotonate to form the enolate with the most substituted carbon-carbon double bond. That's the LDA example. Sodium hydride deprotonates to form the enolate with the most substituted CC double bond. And so if we use hydride to deprotonate that molecule like so, we're going to get that initially. So that's the first step. And then we do our resonance structure of the enolate. There's that carbon-carbon double bond that I was talking about. And so this carbon-carbon double bond is more substituted than the one on the other side, which would be that one. And so sodium hydride is going to produce the enolate where the resonance structure has the most substituted carbon-carbon double bond. And for that reason, that carbon on the right-hand side in this case is going to do the SN2 reaction with the alkyl halide. Yes. Yes, less substituted, less favored. Because that's a tri-substituted CC double bond in the green. And the main example is tetra-substituted. It's got 4 non-hydrogen things attached to it. So give these a shot. Yes. Pitch. Which part? That? All right. So got two options for where to deprotonate here. So we're using sodium hydride. Are we going to deprotonate the left or the right hydrogen? The right. So if we do that, actually, I'm going to draw the enolate just because it's not bad practice. So if we deprotonate there, we get that enolate, which also has that resonance structure. And so that's the more substituted CC double bond versus if we deprotonated The other spot, that would give us that enolate. So this is more substituted CC double bond. Okay, so that means our alkyl group is going to go on that carbon. And what alkyl group is going to go on that carbon? Ethyl. Yep. So you can draw. You can put that, or you could do ET. Or you could go like that. All okay.
So the BR was a leaving group?
Correct. Yep. Instead of iodide, just used bromide. So if you wanted to be official, you could put the Br minus, but nope. Only if I ask you to do the mechanism, which I already said on the announcement is not on the exam, but predicting the products, yes. So all you need to do for, nope. There we go. That's all you need to write for this one.
Right answer, what forgot to take off the leaving group, which you said was option part or?
Forgot to take off the leaving group. Just like put the bromine here or something
Left it on the ethyl group.
on the end of the like here.
Yes.
I mean, I would judge you. I would certainly take off some points. But you would definitely get credit for getting the substitution position right, the right versus the left, which is really the main thing I'm trying to get at with this stuff. But
I just forgot that VR just popped off. We just stayed.
okay, well, I am judging you a little bit, but that's okay. I'm the teacher. I'm supposed to do that. Okay. Oh, I did. Yeah. Okay, that's fine. All right, so sodium hydride favors that more substituted CC double bond in the enolate resonance structure. LDA is bulky. So which hydrogen is it going to deprotonate? Left or right? Which one is least sterically hindered? Right. Yep. So we deprotonate there. You could draw the resonance structure if you wanted, but yeah, whatever. Y'all are slow. All right, and then when we add our alkyl group, what alkyl group is it? Yep. Ew, sorry. Okay, so get our methyl group. And so of course there's various ways that you can write that. You could write it just an extra line. You could write Me. Can write CH3. Any of the above. And speaking of, if you want to give yourself a clue as to which one, just draw out the structure of LDA or sodium hydride. And that might give you a little help. Questions on that? You're not going to forget that LDA is bulky now, though, right? Okay, good. Okay, how do we feel about the problem set? Has anybody started to work on that yet? Yes, the one question. Yes.
It's 9 parts.
Yeah, so your answer, if you didn't see it, if you haven't looked at it yet, it's just one page. And basically there's these 9 different mechanisms that I ask you to draw based on one of the molecules, and then I give you some more to practice with. And then on the second page, there's a sample of what the answers are for the second molecule. Yes, Katie. It's pretty even. It's so it's no 4, but it's four big questions. The first 2 have a lot of subparts. What? Not just 4 questions, but the first including parts, it's 11. Yeah. So there's some predict the products / fill in the reagents or whatever. There is a mechanism, which I sent out in the announcement. You know what mechanism it's going to be. It's the keto-enol tautomerization. Yep, which is either 1 or 2 on the homework. It's going to be one of those 2. And then there's another free response question, which remains secret. Yes.
We plan to give us a full amount. I really struggle with time.
Of time? Yeah. There should, yeah. Oh, you mean the full time for this? Let's see. I think.
Given if we're only 50 minutes.
Right.
But now that. Would you please?
Yeah, I think I have enough time to give Buford extra time. So sure. What? Yeah. Yeah. We can do that. Yes. Yes.
We get like a sheet instead of a cheat note card.
No. You can, however, we'll do an 8.5 by 11 page for the final. Not for this exam. This exam's still note card. But for the final, front and back, 8.5 by 11. Which is rough. It's a little more actually than 3 note cards worth. I don't know about that, but yes. Hey, shut up. The format's going to be different. There's going to be a significant portion of multiple choice, mostly so I can grade it fast because I have to grade it fast. But there's still going to be stuff like predicting the products. What? I have no idea. It's in the syllabus. Yeah, it's at a different time, but it's like 2.5 hours, and so you'll have the full time to do that. It's the 11th. Okay.
11 or 10:45 to 1:15.
Yeah. So it's going to be probably, I don't know, But there's going to be at least one free response. Probably I'll just give you like a sheet of paper to do a free response problem. It'll probably be a mechanism. Yeah.
So is that
Yeah. What?
curve too, like?
Yeah. Everything will be curved at the very end. So the course average will probably be a low B. Yes.
We asked a class about final exam topics.
No.
Take off, sorry. Oh, perfect.
Oh, no, but you reminded me of something. If you do better on, I think I already said this, but if you do better on, so the final will have stuff from the first, second, and third exams and a little bit from the new stuff. But if you do better, say, on the exam 2 material than you did on exam 2, that part will replace your exam 2 score. Only for one exam, the one that benefits you the most. Yes.
If you do well in the last
Not gonna have anybody skip the final. Everybody has to take the final. I know.
So are the last couple classes gonna be like reviews for the final?
There'll be some. We're gonna talk about a little bit of new fun material, which is easy and I think is interesting. Because it's what I did my PhD on, some of it, but yeah. Yeah. About the same. Yeah. Yes. Best way to study, well, he wants to hear the answer to this question. She said, what's the best way to study for the final? To some extent, the old exams, but I would say even more than that, is going to be the lecture notes. I know that's weird that maybe you would think you want to study for past exams, or maybe, I don't know, maybe you don't want to look at those ever again, which I understand. But yeah, there will be a little bit more conceptual type stuff where in the regular exams, you can expect it to apply those concepts while predicting the product or solving a mechanism. But sometimes in the final, I'm going to just explicitly ask you a conceptual question.
You make that really sense for the class.
Yeah.
I'll make like kind of a sample to show you what it's going to look like, because it's going to look different from the rest of the exams. So yeah.
And you said front end.
Yep, because I can't police just front. I was tempted to say just front, but yes. No, this is the last chapter for exam 3, and then there's 2 more little mini chapters that will be on the final, but it's not like I'm going to make the final 50% of the new material, because frankly, it's not quite that important. Yes, unless people have other questions. What? Yeah. Okay, thank you, everybody.